x to the 3/2, and then minus, the only thing left over here is the 2/5 x to the 5/2 plus c. There it is. Okay, what do you think? That's about as basic as it gets. All right, for part B, we have a different looking function. We have 2x plus root x minus 4 plus x cubed, all of that divided by cube root of x. Okay, so Omar, is Omar here?
Yes, sir.
Okay, Omar, I just mentioned that in Cal 1 there's some good things and bad things when it came to the rules we learned. Here we're trying to do an antiderivative. Omar, are you comfortable with the idea that this is a quotient, like we have division, right?
Yes, sir.
So we are not going to look at the numerator and denominator separately and just take the antiderivative of the top and the bottom and just put them as our answer and be done. That would be a major, major mistake, okay?
Right.
So if we don't really have any method yet for dealing with a quotient, do you see, Omar, any way that I can make this not be a quotient, so to speak?
Yeah.
That?
So you turn the 3 radical x into x to the 1/3 power, and
Okay.
then you put to the top by turning it into a negative.
Okay, and then push it to the top? Okay,
Yeah,
so
by turning the power to a negative.
got you. So I think what Omar's saying is instead of writing that, make that x to the 1/3, and then push that up to the top and make it, let me do it this way. Push this up to the top and make it times x to the negative 1/3. I think that's what you're saying. Yes, Omar?
Yes, sir.
Okay, and then what would you do once you've got that moved up to the top? Because now you have a product, Omar. That's what I'm concerned about. You've kind of switched your division into a product, but is there, I mean, can you do that product? Not the antiderivative, but can you actually algebraically do that product? Like, can you multiply this through to each of these?
Yes, I think so.
You can, right? I mean, you should be able to do that. And if you do that, then you have eliminated the quotient and the product. So that will work. That will work. Now, I'm going to do it slightly different, even though that way is fine. I'm going to do it.
I have a question.
Yes.
So basically, whenever we're doing the antiderivative, so we're supposed to get rid of the quotient and the product rule?
Well, if you can. You can't always. In this particular case, we can. And the key to why we can do it is the fact that we have a single term in the denominator. That is what's allowing us to do this. Now, Omar had said, let's take the x to the 1/3, let's move it to the top. I want to just kind of do it a slightly different way. We get the same answer, but I want to point out something algebraically. When you have a fraction and you have a single term in the denominator and you have multiple terms in the numerator, algebraically, you're allowed to split this into now 4 different fractions. You can turn this into 2x over the denominator plus x to the half over the denominator minus 4 over the denominator plus x cubed over the denominator. And I think you can convince yourself of that if you go back to just basic algebra. You can add fractions together if they have the same denominator, right? And if we go backwards, we can pull them apart. And that's basically what I've done. Now what you can do is you can take this x over x to the 1/3 and use this good old property from college algebra that x to the n over x to the m is x to the n minus m. That's a property of exponents. And so what I'm going to wind up doing on that first one is leaving the 2 there. And then I'm going to write x to the, let's see, 1 take away 1/3, right? We're leaving with 2/3. plus, okay, on this one, I have to do a half minus a third. A half minus a third. And maybe I'll do that over here on the side. 1/2 minus a third.
1/6.
Yeah, it comes out to be 1/6. I'm not going to show how to do that. I'm trusting everyone can do that. X to the 1/6. And then minus, now on this one, this next one is a little interesting because you don't have an X on top, do you? But here you just take that X to the 1/3 and push it to the top like Omar did earlier. So that just becomes 4x to the 1/3, negative 1/3. And then finally, we're going to take 3 and subtract a third from it. So what's 3 take away a third?
X to the second.
I'm sorry?
To the second power. X to the second. Taking away a third.
No, it'll be 8/3.
Yeah, careful, 8/3, right? Because you're doing 3 minus a third. So that's 9/3 minus a third, which is 8/3. You just get a common denominator there.
Okay.
Yeah, no, so look, y'all are gonna get really a lot faster and quicker with this fraction stuff. You kind of have to, all right? But this is it. The more practice you have, the faster it'll become. Okay, so we have not taken the antiderivative at all, have we? All we've done is like massaged the function into something we can actually take the antiderivative of. I will also point out that back on Omar's suggestion up here, where he wanted to take this and distribute it through, if you did that, you would get the exact same expression we have. So we'd have the exact same things, all right? I just wanted to remind everyone that you can split a fraction up. If you have a single term on the bottom, you can split it up. Okay, now I'm not going to work the rest of this. Let's just make sure you understand that this first piece is a number in front of x to a power, so we can use the power rule. This is just x to a power, we can use the power rule. This is a number in front of x to a power, we can use the power rule, and then this x to a power rule.
I have a
right?
question.
Yes.
On the green part you highlighted, if you were to FOIL it, would it turn into the f of x that you're doing right now, or would it turn into the fraction you have above it?
No, it would turn into what I have right now.
Okay.
So let me just show you on just one of them. If I were
Okay.
just to take the x to the, oh, that didn't work. If I were to take the x to the 1/3 here and hit this 2x with it,
Uh-huh.
I'd be doing x to the negative 1/3 times 2x. So I'd have a 2, and then
Oh, I see it.
yeah,
Because it's a 3/3 minus 1/3 would be 2/3.
yeah, this right here, we don't subtract the exponents, we
Mhm,
add them, right? So you're doing negative 1/3 plus 1, and that's going to be 2/3.
Yeah. Okay. Cool. Thank you.
That match that. Okay. All right. So I'm gonna say ... meaning you could take that the rest of the way. All right. Next page, or next problem and next page. We have a function f of x equals sine x plus secant x tangent x. All right. Okay, Abe, you're up.
Yep.
Okay, Abe, what are you thinking?
I think we need to find a relationship between the sine and whatever's next, I think.
Okay, so what do you mean? I'm not sure I follow you.
So I don't know if there's any identities that we can use to break the secant squared and tangent squared, or maybe we just need to go straight to the derivative or antiderivative.
Well, you have a plus here, don't you?
Mm-hmm.
So you can just think about these separately, right? Like what's the antiderivative of that? What's the antiderivative of that? So you are allowed to just think of them separately.
Mm-hmm.
So do we know the antiderivative of sine of x?
Yes, it should be minus
Mm-hmm.
cosine of
There
x.
you go. Well, minus cosine x. So that first one's not bad. Now, how about secant x tangent x?
Well, that's a product.
It's a product, right? It's a product, but just go back to Cal 1. Can you think of any function from Cal 1 that when you take the derivative of it, you get secant x tangent x?
Cosecant?
Close. So yeah. So yeah, you're looking for your formulas. That's good. That's what you would need to do. Okay. But this is one that we have a formula for. This is actually the derivative of secant of x.
Okay.
So the derivative of secant of x is secant x tangent x. So even though we have a product, right, there's multiplication right there. Even though we have a product, the fact that it is the derivative of something we know, we can just put the answer. All right, so there's really not a whole lot of work that we needed to do for that one. That was just how much do we know about the derivatives of the trig functions. Okay, let's look at D. F of x equals 2 plus x squared over 1 plus x squared. I'm gonna let you look at that. I've got to go blow my nose. I'll be right back. All right. Anybody have any ideas?
Do we try this as u and v and get the u and u prime and v prime?
Okay, so if we were trying to find the derivative of this, then we would use like quotient rule. I don't know if that's what you're saying. But we're not trying to find the derivative. We're trying to find the antiderivative. And as of right now, I have shown you nothing in terms of how to find the antiderivative of a quotient. Okay, and I'm going to tell you right now, there is no like formula, right? We have a quotient rule for derivatives in Cal 1. In Cal 2, there is no quotient rule to go backwards. It's not there, okay? And that's what's going to make this hard. So how about what we did last time on the last problem? Omar had said, let's bring the thing up to the top, but see, we have 2 terms in the denominator, right? That's different. So we'd have to bring the whole thing up, and then you can't multiply through. So let me just write it down so you'll see what I'm saying. If we brought the denominator all up, then it would be like this, and you cannot like multiply this out. You can't FOIL this, and the reason why is because of that power. So that's not gonna work.
Separate the 2 and x squared maybe.
Over the denominator?
Can't you like factor them?
The numerator.
Do you mean this? Like take the 2 and put it on top of the denominator?
Yeah.
And take the, yes, that is allowed. That is fair. I mean, now I'm not saying it's right, or I'm not saying it's going to get us to the answer, but I am saying that that is a legal move, right? That is a legal algebraic move. So by doing that, do we gain anything? Do you see that we can do anything with this?
Can you cancel the x squareds on the right?
Can you?
No, we can bring the bottom, the 1 plus x squared, up with a negative sign.
We could, but let's go back to that other question about the x squareds, canceling them first. Can we do that?
No, we can't do that because they're being like
It'll
they're
just be a
part
one.
of they're being added to 1 and 2.
Yeah, so those don't cancel. Now, you know, when I was a math student, I would run into things like that where maybe I wasn't sure if I could do that. And anytime I wasn't sure, I would just try an example. Like I would just like plug a number in there. Like, let me just take this expression and plug in 2 for x. If I do that, I get 4 over 1 plus 4. That's 4/5, right? But if you cancel these x's, x squareds, then what would you get?
0 over 1.
Yeah, I mean, I don't know. It depends on how you cancel on top. If you cancel and make that a 1 and make that a 1, then you might be saying that that's 1/2, but it's not. It's 4/5. There's no way around that.
But can
That's
we
not-
cancel it? Because
No, you cannot. No, you cannot cancel it. All I'm trying to do is illustrate, like, if you're not sure, give yourself a value of x and see if it makes sense. So we can't cancel the x squareds. Someone said we could bring the 1 plus x squared back up to the top, right? You could do that. I'm not sure what we gain again. Because we bring that up. I hear someone saying, so, oh, I forgot to put plus there.
Is this the case when we use
factor
natural
one.
log?
Okay, no natural log yet. And someone else was saying something?
Factor 1 maybe, and make it the numerator, factor 1 out of it. Say, because 2 and plus x squared, there is 1 there, so you say 1 parentheses 1 plus x squared, so that you cancel 1 plus x squared.
You're saying rewrite this 2 as a 1 plus 1?
Yes,
And
and then plus x squared.
And then another one like this? I'm not sure if that's what you're saying. Well, is that true? Do you believe that that's true?
Yes.
Okay, now, do you recognize this? Do you remember a formula I gave you when I put like 5 stars on it?
That's tangent x. That's the derivative of tangent x.
That is arctangent of x. Okay? So the antiderivative of this, so right now here's what I know. The antiderivative so far would be the antiderivative of that, which would be arctangent of x, plus, and then I'd have another arctangent of x, and then plus, and now I have to do this, but that I don't know. Because that's not arctangent. Y'all see what's happening here? Following me so far? Okay, so maybe,
I'm not sure. How did you get the 1/1 plus x squared?
by rewriting the number 2 as 1 plus 1, and then putting each of those on top of the common denominator.
Okay.
Yeah. Now, that wasn't my idea. I'm just following someone else's lead, but it's getting us somewhere, right? So look, I want you to think about this right here. Could I rewrite that as x squared times 1/1 plus x squared? Could I do that?
Yes.
Yes.
Yes. Okay, now, could I then just find the antiderivative of each of these separately?
Yes.
Not with our rule. With the
No.
product.
Okay, look, Cal 2 would be so much easier if that's the way it was, but it's not. See, why can't we do it? We have a product. And when you're trying to undo a product, you cannot just do each one separately. You can't, okay? You can't do it. So that looked a little promising, but it didn't work. Now, I want to point something else out while I'm doing this. You see this one right here that we had split 1 and 1? Could I have taken that and rewritten that as 2 times 1/1 plus x squared? Could I have done that?
Yeah.
Yes.
Okay.
No.
Now, can you take the antiderivative of all of this? See, this is a constant, isn't it?
Mhm.
So it should come for the ride. So it should give us a 2 times, what's the antiderivative of that? Arctangent of x, right? That's the same as this, because arctangent of x plus arctangent of x is 2 arctangents of x. So we get the same result, right? So we're stuck, aren't we? We're stuck. We're stuck right here. This, we are stuck. And getting like partially there is not enough. We have to get all the way there, right? So here's what I'm doing. I'm gonna start over. There's a reason why I give this example. Because the way I'm going to do it, I'm going to do it two different ways. The first way, I think you'll be like, okay, well, I hadn't thought of that, but now that I see it, okay, you know? And then the second way I'm going to do it, you're going to be like, man, that's tricky, you know, and you're going to probably be a little bit upset about it, okay?
Yeah, I was going to ask if you could use the useful version of 1 from the start.
Yeah, something like that. I'm going to do something in the same ballpark as like just being, I'm just going to be clever, okay? Just going to be clever. Now, I'm not saying that I'm clever. I'm saying that I was once sitting on your end and someone else showed me how to be clever, and then I became more and more clever the more problems I did, all right? So here's the first approach. The first approach is first to make sure that I understand that I can't really do anything easy algebraically. So I'm going to pull out, let me get my little toolbox here. Oh, it's right there. It's long division. I'm going to take the long division out, okay, and I'm going to start using it. Ready? So I'm going to do the numerator divided by the denominator. The numerator is this. I'm going to put it in descending order. Here's my denominator. And then I get to play the good old long division game. And maybe it's been a while. You got a lot of cobwebs. I mean, I could barely find the tool. It was sitting over here in a box. So, but you need to be able to do it. You're a Cal 2 student. So we ask ourselves, what do you multiply x squared by to get x squared? And that's a 1, right? We need 1. Then you multiply 1 here, and you put that underneath. Then the very important line, you subtract. So you change the signs. That becomes minus, and then go ahead and go down. X squareds cancel, 2 minus 1 is 1, and we continue. And we ask ourselves again, what do I multiply x squared by to get 1? And at that point, you have to stop because you can't make x squared turn into 1. So the 1 is your remainder, isn't it? So what I'm going to do now is I'm going to put, okay, plus the remainder 1 over the divisor, which was x squared plus 1. And that's it. That's the long division. So what this means is this. The original function f of x could be rewritten to be this. 1 plus 1 over x squared plus 1.
Why didn't you use a 0x in the, when you were like using the long division? Because I think I remember it was x squared plus 0x plus 2.
Oh, you could do that. Yeah, you could do that. I kind of got lucky that there wasn't, that no x terms just showed up. Had there been an x term, I would have been in trouble. I think what you're saying is like, why didn't I put like 0x then plus 2 here like that?
Yes, sir.
Yeah. Oops. I kind of like got a little sloppy there. But I got lucky also because there were no x's when I did the multiplication.
Okay.
Okay, so here's where we are. Now, can you find the antiderivative of that? Let's see. Monado? Is it Monado?
Yes.
Okay. How do you feel about taking the antiderivative of that?
Yes, it's possible.
Okay, so you can do them separately, can't you?
Yes.
So what's the antiderivative of 1? So think about it. What do you take derivative of to get 1?
X.
X, okay. And then plus, now this next one?
Arctangent.
Arctangent.
And then plus C.
Plus C. We're done. Boy, that was a lot easier. Just that one quick long division in the beginning made it really kind of trivial, didn't it? But it's the whole like actually getting the long division out and doing it and trying it. Okay, so that's the way that's kind of like, all right, now you see it. Now you know long division's on the table. Now the clever way. I'm going to start at the beginning. What I'm going to do though is I'm just going to be really tricky. I'm going to do this. 1 plus x squared over 1 plus x squared. Okay, so Aisha, I believe that's how you said it. Aisha, I think, suggested that we split the 2 into a 1 plus 1 earlier.
Yeah.
This actually would, if you would have done that in the beginning, like I just did, instead of after we had split it, then check this out. I'm going to write this on top of this, and then I'm going to write this on top of this. Kind of split it into 2 fractions now. So if I split that in 2 fractions, I get 1 over 1 plus x squared. And then I get plus, now what's 1 plus x squared over 1 plus x squared?
1.
1, okay. We're there. This is this. So I actually didn't even need the long division.
Would this way work with most of the quotient rule?
We
No?
got lucky. We got lucky. This would not be something that, I'm not sitting here saying like, from now on, you never have to do long division because you can always do this. This one just happened to work out.
Yeah, okay.
Yeah, good question. All right, so that's it with the examples. Of course, you're going to need to do your homework where you're just going to have more, you know, enjoyment of just working through all these little algebra things that you have to get kind of straight with. But we're going to move on to one application of this, and then we're going to be done with 4.7.
Sir.
All right. Yes.
Do you think you can do one that like has like a longer like denominator or like something like very similar to that, where like it's set up like a quotient, it's just like bigger, you know, something a little more complicated?
Well, I can't really give you anything that's right now. The only thing I can give you has to be something that you can either rewrite as powers of x, like the second example we did, or you're going to have to be able to somehow like use long division or something in order to figure it out. And even then, the only thing that saved us with the long division is that we had the 1 plus x squared on the bottom. If that was 1 plus x cubed, we're done. We're stuck. We can't do it. Okay. And so right now, like we have a very limited amount of stuff we can do. So I'm hesitant to try and give you something harder because you know.
So in the homework, they're going to be similar to this?
Oh yeah, every problem in the homework, you have to keep that in mind. You really don't have a lot that you can do. So the algebra is going to be there. Okay, like somewhere in there, you're going to be able to simplify.
Okay.
Okay.
Yes, sir. Thank you.
Okay. All right. So the next topic has to do with something that hopefully you remember from Cal 1, and I hope that your professor made this clear, that if you have a position function of an object, so where you have time as your x-axis and distance is your y-axis. So let's say we have some function in here. We'll call this function s of t. That's the standard notation we use for a position function. So you give me a point in time, plug it into the function, I'll tell you how far that object has gone. In Cal 1, we learned that if we take the derivative of this function, we get a new function, s prime of t. And that function is the what function? So if the original function is position, then the derivative is your velocity function. So your x-axis is time and your y-axis is the velocity of the object. And then if you take, and we call that, we have a notation for that, we call that v of t for velocity. So the derivative of the position is the velocity. And then if we take the derivative of a second time, we get a new function. That's your second derivative of your position, which is the, anyone know?
Acceleration.
Acceleration function. And we call it a of t. And that gives you time, and here's acceleration. Okay, so hopefully you remember that from Cal 1. Start with the position function, take its derivative, you've got velocity, take its derivative, you've got acceleration. Right? Okay. We're gonna work with this, but I just want to point something out that's kind of interesting, I think. When you go back and you look at your original position function, let's say we take a point on that position function and we look at the slope of the tangent line there. The slope of the tangent line would be the velocity at that point of that object. That's what the slope of the tangent line would be. And when we talk about slopes of lines, it's always rise over run, right? Rise over run. So when we look at rise, for us in the position function, rise is distance and run is time. So the unit that we would get for the derivative, the slope, the unit we would get would be distance over time. In other words, it would look like maybe like miles over hours. So over here, this velocity is going to be miles over hours. Now, if I take a point on this velocity function, take its derivative and look at its slope, it's going to be rise over run again. So it's going to be velocity over time, but velocity is miles per hour. So you get miles per hour over hours again. And that's why acceleration, I'm only bringing this up because I know that in like physics, you're taught that the acceleration of gravity or something like that is negative 9.8 meters per second per second. Have you all heard that before? Like per second per second? Like why is it per second per second? Well, it's because you're doing on the first derivative, you're doing distance over time. So your first derivative is a speed, right? Miles per hour. But then when you do this, the derivative a second time, it's miles per hour per hour. You have to have that per twice. Okay, I'm going off. Let's just move on. Okay, so if we have position, we have velocity, and we have acceleration functions, right? If we start with position, we can get to acceleration. Can we start from acceleration and get back to position?
We can, but we would have to use antiderivatives.
That's right. If I start here in the yellow, okay, if we start there, the question is, can you get back to this one? Can you get back to position? So think about this, because I can remember when I was a student learning this, okay? I can vividly remember this. I was in the car with my dad, and I just learned this. And I said to him, I was like, man, it's amazing that if you know an object's acceleration at every point in time, that you can actually figure out where it was at every point in time. I mean, that is amazing to think of that. If all I tell you is what the acceleration of something is at every point in time, that I can somehow go back and tell you exactly where it was. Does that seem like really troubling that that would be possible?
Pretty cool.
It's cool, but does it seem like it's possible?
It doesn't seem like the only troublesome part is that like to go from position to velocity to acceleration, we're taking 1 point at a time. So it's a lot of work to like work backwards in a sense,
Yeah.
if you want to find all the points, you want to do all that.
Yeah, think about this, okay? Think about this. If I take this pen, okay, and I just drop it, okay, as soon as I let it go, the only thing acting on that pen is gravity, right? The acceleration of gravity. And every object that you drop on Earth has the same acceleration function. Okay, so on Earth, okay, on Earth, the acceleration of an object at a given point in time is negative 9.8 meters per second per second. So the acceleration function on Earth is a constant function. Do y'all see that? Things, I mean, as long as you're on Earth and you drop something, everything is under the same acceleration. How in the world can I tell you the acceleration function and then you go back and tell me where that pin was? Right? That seems very, like, how in the world are you gonna do that? But it's possible. But there's a little catches, okay? There's a little catch to it, because think about this. If we start with the acceleration function, when we do the antiderivative and go backwards to velocity, we're gonna have a plus c, aren't we?
Oh, yeah.
And that plus c means that we're gonna know the answer, but it's actually gonna be a family of functions, right? And we don't actually know which one it is. We don't know which one it is, do we? But I could actually find it. I could tell you which one it is if you just give me one piece of information, okay? So you give me the acceleration function, give that to me. I will take the antiderivative. I will be able to come up with a family of velocity functions. And all I ask of you right now is that you just please tell me what was the velocity of the object at just one point in time, okay? Give me that piece of information. So if you were to give me that, do you see that if you tell me now, hey, like at 2 seconds, it was going 30 miles an hour, then I would actually be able to go to 2 and go up to 30 and be like, ah, that's the one. It has to be that one, you see? And then I've nailed down the exact velocity function. And then we do it again. We find the antiderivative, we go back to position. This gives us a whole family of curves again. So what do you think I'm going to ask you for?
Where was the location at a certain time?
Yeah, just give me one point in time. Tell me where it was. Give me 1 point in time. Give me one point on, 1 point on the curve, and I will be able to nail it down. And then I will have the position. So in summary, okay, in Cal 1, if you start with position, you can go and get the velocity function, and there's no question about what it is. It's only one function. You've got it. You don't have to do any more work. Then you can take derivative again, you can get the acceleration function. You will have it. That is the one. But in Cal 2, when we go backwards, we start with acceleration, we go back to velocity, we're going to need just one piece of information about that velocity function. And then we go back to position, and you're just going to have to give me one piece of information about the position. So it's a little bit more than just saying all you need is the acceleration. You need the acceleration and 2 points, one on the velocity function and one on the position function. If I have that, I'm in business. So let's do a problem. If the acceleration of an object moving in a straight line is this function, a of t equals 24t minus 6, and we're also given s of 1 is 7, and v of 2 is 41, then we want to find the position function first, and then we want to find s of 2. S of 2 means tell me what its position was at 2. All right. So first things first, we need to get to the velocity function. So let's do an antiderivative. The antiderivative of that would be the velocity. And let's see here. Maria, where's Maria? Maria here?
Yes, I'm right here. Hi.
Oh yeah, I'm sorry. You go by Celeste?
Yes.
Do you prefer Celeste?
Yes.
Okay, let me take the other part off then.
Thank you.
Yep. Okay, so Celeste, antiderivative of that? So
Of the 24t?
24 is going to come down, right? And then what's the antiderivative of t? So that's t to the first power. So do your little power rule there.
I know it's not 1, right?
Okay, so the
For me, it's
formula-
difficult to take the antiderivatives.
1 over.
It's 1 over
the power.
yeah, the 1 over t 1.
There we go. And then t to the 1 plus 1 also,
Yes.
right? Okay.
Yes.
And then we have minus. Now, what's the antiderivative of 6? So what do you take the derivative of to get just 6?
It will be like a 6x or something like that.
Yeah, 6x, but in this case, it'd be 6t because our variable's t.
Yes.
Plus c. Agreed?
Yes. Yes.
Okay, so let me clean this up. This is 1/2. So half of 24 is 12. 12t squared minus 6t plus c. Okay, so what we have now is we have the antiderivative, we have the velocity function, kind of. we have a whole family of them, all right? So we need to figure out if we can nail it down. Can we figure out what that c is? If we can figure out what the c is, then we would know exactly what the velocity function is. But Celeste, do you see that they tell us something about the velocity?
Yes, at 2 it equals 41.
At 2 equals 41. That means if I replace these t's with 2's, right? So of 2 being equal to 41 implies that when I replace all of these t's with 2's, 12 times 2 squared minus 6 times 2 plus c, that should spit out 41.
Yes.
And so let's do the math there. 48.
And then you just solve for that, correct?
Yep, we're going to solve for c.
5.
So 8 minus 12. Go ahead, what?
I said 5 for C.
Oh, it's 5. Okay, so I believe you. It's 5. So, hold on. The computer screen just turned off. All right. Everything's still there. Okay. So here's what we know now. We know the velocity function, and now there's no question about it. It's 12t squared minus 6t plus 5. Okay, so there's our velocity function. We started with acceleration, went back to velocity, used that point that was given to us, and now we know the exact one. And now we just get to play that game again. Okay, we need to go from velocity back to position. So we've got to do another antiderivative, and James is going to help with that. So, position is x. Go ahead.
T. So same thing that we've already did. So the constant comes down for the ride.
Okay.
The 12. T1. 1 over 2 plus 1, right?
Yep.
So 3, and then the it's n plus 1 for the top, so t to the third.
Good.
Minus the constant comes down 16. Yeah, and then 1 over
1 plus 1.
1 plus 1. Okay, so yeah. Then the constant, the 5 just
T
comes
squared.
down with it. Oh,
yeah, so 5, the
okay.
antiderivative of the 5 is just 5t. So just get used to that, everyone. The antiderivative of a constant, antiderivative, not derivative, is always just the constant times the variable. So the antiderivative of 5 is 5t. The antiderivative of -2 is -2t. Antiderivative of pi is pi t.
Pi t.
Pi t. Well, depending on the variable. In this problem, it would be t. All right. Now we have plus a constant, right?
Yeah, plus.
Okay. Now I could use c again. All right. I could use c, but I'm going to use d instead. All right. Y'all give me just a moment. Y'all go try now and use this point right here. Just want to make sure this is not an emergency.
Sure.
Okay, sorry about that. I'm just going to work it out here while y'all are thinking through it too. Oh, we should have cleaned up that derivative. I'm going to clean it up first.
Would it be
So
like
in terms
4t
of
cubed?
t, are we supposed to put the 1 in terms of t?
Yeah, that's what we're
Equator?
going to wind up doing. Yep. We're going to use the fact that when you plug 1 into this, it should spit out 7, right? Okay, so now using the fact that s of 1 must be 7, what we get
So that,
is,
oh, yeah, I'll let you work through that. I'm already, We
You
gotta find
already
that
got it?
constant. I found the constant of
Okay, what
D.
did you get?
I got 1.
That D is 1?
Yeah, that's what I got.
1, 6, yeah, so we should get 6 plus D is 7, so D is 1. And
So
that
then
allows
just go in and then plug in 2 for T instead. Well, since we know the constant now, and then that'll
That's
give us
right.
our. Okay.
Good, yeah. So this right here, replacing D with 1, that gives us the exact position function. And so what's great now is we can find the position of the object at any point in time, right? Because we have the actual function. So part B of this problem is just to find S of 2. So you just plug 2 into that and get an answer, which I'm not going to do. Okay,
I have a question.
yes.
In like quizzes or exams like that, with those problems, are you gonna give us those 2 points like for the velocity and position?
I have to, or else
Okay,
you can't
good.
do it, right? Now,
Yeah.
I have to show you something because there's another type of problem that you can get, and you'll see it in your homework. It's a little bit more difficult than this. So let's say we go back and we look at this problem again. Just gonna use the same one. But this time, instead of me telling you that S of 1 was 7, and before I told you that V of 2 was 41, right? What if I tell you that S of 3 is 10? I've given you no information about the velocity function, have I?
No.
No. Okay, so here's how you would do this. First
But
thing you do is
that's okay, right? Because then we take the derivative going like forward from the position, and then it'll give us our velocity since we're taking like the instantaneous velocity on that point, right?
well, we can't get to the position function because we can't nail down what C is on the velocity function,
Okay. Okay.
right? Do you see that? Like here we started acceleration. We take the antiderivative, which we did in the previous work, right? So I'm not going to redo it. And then at that point, we were able to find C, but here we can't, can we?
No.
So it's okay. Just do the antiderivative. The antiderivative of this, sorry, would be a position. Our position function would be, so we do the same thing, power rule on this and all that, we should get 4t cubed. We do the antiderivative of this thing, and that should still be 3t squared. But now, what's the antiderivative of C?
D.
No. C is a
yeah,
constant.
CT.
CT.
Or CX, CT.
And then plus, now the constant from the antiderivative we just did.
Which is D.
We'll call it D. Now, you have the position function, right? But you don't know what C is, and you don't know what D is. There's 2 things you don't know, right? But you do have 2 pieces of information about the position. First thing you know is that S of 1 is 7. And that means that when you replace all the T's with 1s, be careful here, replace the T with 1, it just becomes C times 1 plus D. You get, what do you get? You're supposed to get 7, right? Y'all see what I'm doing? So what does that turn out to be? 4 minus 3, that's 1, right? Take the 1 to the other side.
C plus D equals 6.
C plus D is 6. Now, we know from algebra that you can't solve an equation.
Oh, you do the 2
without one
equations,
variable.
right?
Yeah, but we have 2 pieces of information. We have that S of 3 is 10. So the fact that S of 3 is 10 means that, oh shit, I got to plug 3 in there. Okay, so 3 to the 3rd power is 27 times 4. What is that? 100.
108.
108.
108.
108 minus, okay, we're plugging a 3. We're plugging a 3 in here. 9 times 3 is 27. Y'all see what I'm doing? Plugging a 3 in there. What's that? 3C?
81 plus
Plus.
C. Oh yeah, the T for the C. Oh, forgot about that.
Plus D must equal 10. Is everyone clear? All I did was I plugged 3 into that function up there. Let's clean that up. What do we
So
get?
108 minus 27 is 81. And then you subtract 81 from 10. So you get negative 71.
You should get 3C plus D equals negative 71. And now what we have from college algebra is a system of linear equations. We have that C plus D is 6, and we have 3C plus D is negative 71. And you can solve that system of equations using one of two methods, substitution or elimination, which I'm not going to do. Understand though? Okay. So Celeste had asked, I think in the beginning, will I always give you that information, right? I will, but it could be possible that I give you, instead of a point of the velocity and a point of the position, I may just give you 2 positions. And that would force you to do a system of equations. So make sure, I would finish this problem on your own. I would make sure you do your homework where you're given a problem that's similar to this. Okay, we all good? I do want to point something out. For those of you who have taken a physics class, you may have seen a formula like this before. This is a formula that we use in physics to talk about if you take an object and you throw an object, let's say off of a bridge or a building or something like that, and it starts falling on Earth. This will give you the position, or it'll give you the height of the object after t seconds. Now, this formula is used if we have to neglect air. We have to take air out of the equation. If you put air in, it becomes a little more complicated. But if there's no air, all objects on Earth fall at the same rate. And so the height of an object after a certain number of seconds is given by this. Does that look familiar to any of you?
Yes.
Yeah.
Okay, this D naught right here, this right here is your starting height. That's how high the bridge is, but that's how high the building is. And this V naught right here is your starting velocity. So it's like if I take my pen and I just let it go, then the height off the ground is my starting height. If I just let it go, then my starting velocity is 0. But I could also like throw the pen down and then I gave it a starting velocity of something other than 0. Or I could have taken the pen from this height and threw it up. I threw it up and it went up first and then came down. This formula accounts for all of that, okay? It accounts for everything. Here's what's, I think, mind-blowing about this. If you drop something, we already talked about it. Once you drop it, what's the only force acting on it?
Gravity.
Gravity, okay? So what I can tell you is that if you have any object on Earth, the acceleration function for that is a constant, negative 9.8 meters per second per second. Now I'm going to convert that over to feet. So if you convert 9.8 meters over to feet, you get about 32 feet per second per second. So I just did a conversion for us real quick. So let's start with that. Let's say we have we know that the acceleration of an object is 32. Can somebody tell me what the velocity function would be then?
32t plus c.
32t plus c. Now, out of curiosity, what would the velocity of our object be at 0?
C.
C.
It would just be C, right? So V of 0 would be C. So let's not call it C, let's call it V sub 0. Because that means it's our initial velocity, right? Now let's take the antiderivative again. The antiderivative of this would be our position function. I'm going to call it d of t instead of s of t. What's the antiderivative of 32t? Oh, that was supposed to be negative 32. I apologize, negative 32.
Negative 16t squared.
Negative 16t squared plus, what's the antiderivative of v naught?
V sub 0 t.
Oh, v naught t.
Plus some constant,
D
right?
naught.
Which I'm going to call d. But what can you tell me about the position of the object at 0?
D.
It's d. So let's not call it d. Let's call it, you're saying that at 0 the position is d. Let's call it d naught. Right? And what do you get? That's this. Right? So this formula isn't some magical result of like crazy math. It's just knowing the acceleration on Earth. If you know the acceleration of gravity on Earth, you can automatically recover the position function. Now there's some other things we need to know. We need to know the starting height and the starting velocity, but other than that, we've got it. This would also work on Mars and the Moon and any other planet that had gravity. As long as you have an acceleration function that you can measure, then you can recover its position function. It's independent of Earth. Does that make sense? So the only part of this formula that would change, the only part that would change if you were on the Moon would be that number. It wouldn't be negative 16 anymore, right? It would be half of the acceleration of gravity on that planet, right? Because ours started out at 32, and when we did the integration, we wound up with half of it. That's kind of cool, right? But you can do that pretty much anywhere you want. Okay, we're moving on. We're ready to start the next section. 5-5. So 4-7 really is about you taking the time to get comfortable with the power rule. That's really what it's about. And just getting where you're getting faster with those fractions and being able to do that quickly. All right, so 5.5 is called the substitution rule, which we're about to get to. But before we get to it, we're going to get some notation out of the way. So right at this point, if I want you to find the antiderivative of something, I have to like explicitly tell you to do it. Like I need to like write down the function, then I say, hey, go find the antiderivative, right? Well, we need a better notation. That's something shorthand that I don't have to write it down. So like just like in Cal 1, when we had a function f and I wanted you to find the derivative, I used a little prime mark. Or maybe we did derivative with respect to x of f or something like that. There was something that I could write that would let you know to take the derivative, right? Well, now we're going to come up with some notation that will tell you, hey, look, it's time to take the antiderivative. And the notation we use is over here. We use this, it's like an S that's been stretched, okay? So it's like an S that's been stretched. And then what you do is you write the function down, whatever the function is. And then next to it, you say times dx. And that right there is telling you, when you see that, it's telling you to look at that function and find its antiderivative. All right? That's what it's telling you. The piece here, that symbol is called the integral, or the indefinite integral. I'm sorry. That's called the integral sign. All right? That's called the integral sign. This is called the integrand. This is all in the notes, right? Y'all can see that there. The f of x is the integrand. The dx is called the differential. Now, don't let that freak you out. Don't let that freak you out. I'm going to try and explain where that differential comes from. So let's say we take an example back from Cal 1. Y equals
what was
x.
the name of the last part?
Differential. It's written over here on the side in the notes.
Okay.
You see it over here? Called the differential.
Yes.
Okay, so if we go back to Cal 1, let's take a look at this here. If I say, take the derivative with respect to x, we would have dy dx on the left, and on the right, we would have just 2x. We all agree? Now, if I multiply both sides by dx, I would have 2x dx, wouldn't I? Just like multiply both sides by dx. So what you're seeing, what I'm telling you is that when we've taken derivatives and got an answer, sitting next to every single time we've done it, sitting next to it, we could have brought the differential over. We never really did, but in this notation that we use for antiderivatives, we'll always include the differential over there. And the reason why is because the differential tells you what variable we're differentiating with respect to. Or sorry, which variable is the function is with respect to, which is going to turn out to be vitally important to us. All right. All right. This when you do this, you find the antiderivative, right? So this right here is called the indefinite integral. So I'm referring to my notes over here. The whole thing is called the indefinite integral. There's the integral sign. That's the integrand. That's the differential. And when we find the antiderivative, we know we've always called that capital F of x, and then we've always thrown on this c. Well, the capital F of x is called the antiderivative of little f, but the c, we actually have a name for it now. It's called the constant of integration. And the actual process of finding antiderivatives of functions is called integration. All right, so when you were in Cal 1, you were doing derivatives, and that's called differentiation. Now we're in Cal 2, we're doing antiderivatives, and that's called integration. And a lot of times, if you look at a calculus book, or if you think about calculus on like the big picture, usually calculus is split into 3 classes. You have Cal 1, which is differential calculus. You have Cal 2, which is integral calculus. And then you have Cal 3, which is vector calculus. So in 1, you learn how to differentiate. In 2, you learn how to integrate. And in 3, you do both differentiation and integration using vector functions in vector spaces and vector fields. So you just basically, the good news is in Cal 3, if you take it, there's no like new operation. It's still just differentiation integration. It's just now your functions are different. You're allowed to be outside 2-dimensional space. You can be in 3-dimensional, 4-dimensional.
What's a vector?
Well, we started talking about that at the end of class last time. Vector is a little complicated, but in terms of vectors here in calculus, vector is an object that has a magnitude or a length and a direction. So
Okay.
anything that has length and direction is a vector. Yeah, I could go on. I'm not going to though.
Okay.
Okay, so that's just notation. And now we have, with that notation, we can see this power rule that we've already learned. We can see it written with this new notation. So what is the integral of x to the n with respect to x? It is equal to 1 over n plus 1, x to the n plus 1, plus a constant of integration, so long as n is not equal to -1. And it's the natural log of the absolute value of x plus a constant of integration if n is equal to -1. So this is just a slightly different notation. All right. At this point, you should become familiar with formula page 6, numbers 1 through 20. I'm talking about this page right
What
here.
section are we on right now?
5.5. But really, the notes I'm doing right now are probably not in the section 5.5 in the book. I doubt they are. I actually haven't started the 5.5 yet. Like I'm just getting us ready for it. So these formulas right here, you should become familiar with. Now, at this point, formula number 1, just ignore it, okay? That's an entire section we have to do, all right? So don't worry about formula 1. Does formula 2 look familiar? Formula 2 is the power rule. Now, do you see that in these formulas, they're using u instead of x? Do you see that instead of using x, they're using u?
Mm-hmm.
Okay. Numbers 2 and 3 are basically the rule I just had up a second ago. And then the rest are things that you should know. What's the antiderivative of e to the u? Oh, e to the u plus c. What's the antiderivative of sine of u? Oh, negative cosine u. What's the antiderivative of cosine u? Oh, sine u. So these all, just be aware that these are here. Formula 17, we're going to use a lot. So I don't want us to sit here and try and memorize these right now, and I'm not asking you to memorize them. I just want you to know they're here, all right? Because I'm going to be pointing back to these later. All right, now I'm ready for substitution. I'm just going to go to a full page. Do I want a full page?
So we're actually done with the different the antiderivatives
For now.
Okay.
No, we're not done with antiderivatives.
Antiderivatives are integrals.
Yeah, it's the same thing. An antiderivative is an integral. Like when you do integration, you are actually finding an antiderivative. We're just using different language and different notation.
Okay. So what I meant was like the section 4.7 actually.
Yes, that we're done with.
Okay.
Sure, and this can also be used to like find the area of like a space like in a graph, right? Like.
Yep.
Okay.
And
I
that's
think
all
we did this in Cal 1, like we touched it.
Yeah, so in Cal 1, a lot of times we do these and we start to talk about the area stuff. In Cal 2, what we're going to do is we're going to make sure that you can do antiderivatives, not of easy things, but of hard things. And then once we get through all the hard stuff, then we say, okay, let's go use this for something. Let's go do let's do applications. Okay. So we've got to suffer here for the first time we will actually do antiderivatives is in October. Okay, that's the actual time. That's the first time we're going to actually start talking about areas. It'll be in October. We've got to get through all of September before we can start doing that.
So, real quick question: when we're evaluating the definite integrals, will we also go over the Riemann sums right there?
We will talk about Riemann sums. Yes. Mm-hmm. Okay. Yep. That's how we're going to introduce it. Actually, we're going to start with Riemann sums, and then from there we're going to get to the fundamental theorem of calculus, and then we'll have the formula for finding areas under curves. Okay. All right, here we go. So our goal right now is to find antiderivatives and of things that we can't do up to this point. All right, so something we can't do. So the way I'd like to motivate this idea is by let's start by going backwards. I'm going to give us a function. We're going to differentiate it. And then we're going to look at that answer, and then we're going to try and find the antiderivative. Okay? So let's just start out with something like this. Y equals arctangent of sine of x. Okay, I'm not asking you to find the antiderivative. I want us to actually take the derivative of this. Okay? So let's take the derivative. The derivative of that would be, okay, what's the derivative of arctangent of something? 1 over
1 plus x
squared. 1 plus whatever's in there squared.
Squared, so sine squared x. Chain rule times derivative of what's in here, which is
cos
x. And I'm just going to clean that up and just put the cosine on top and do this. There we go. Okay. Do we all agree that that's the derivative of arctangent of sine of x? All right, now what we're going to do is we're going to act like we didn't do that. Okay. And we are going to try and find the antiderivative of cosine x over 1 plus sine squared x dx. Okay, so what you see in yellow here is just, again, that's the thing, that's the notation that's telling you, go find the antiderivative, all right? Now, do we know the answer? The answer is arctangent of sine of x plus c, but we're acting like we don't know that, right? So how in the world are we going to get back to that, right? If you think about what we've learned up to this point, this definitely is not like a formula we should know. It's not a power of x, right? So we can't use a power rule. Do you agree? And that's all we have, right? It's either something we know or it's the power rule. That's all we have. So maybe there's something we can do. Can we split it into two fractions?
I think we can.
You have a single term on top and two on the bottom. So you cannot split it. It's kind of like this. If you have 1 over 2 plus 3, you are not allowed to make that 1 over 2 plus 1 over 3. Like, that's no go. Right? So we can't
Oh, yes, yes.
You could,
split it.
well, you can technically multiply like what you did up there, cosine by 1 on in the numerator. That technically splits it.
What do you mean?
Like what
Oh,
you
you
did.
mean-
Yeah. You just multiply cosine by 1, and then that splits it.
You mean like this?
Yeah.
Oh yeah, that we could do. That we could. But then you can't do these separately, right? You can't find the antiderivative of those separately because there's multiplication between them, right?
Mhm.
Okay, so we first look at this and we're just kind of like scratching our heads, right? Well, we have a method. It doesn't always work, but it's a method that you're now going to learn. It's called substitution, often referred to as what we call U sub. U sub. So here's the way U sub works. I'm going to give you the steps, and they're weird. There are the steps right there. Step 1 is we are going to look at the integrand. Okay? That means look at this thing. Look at it. Focus. Concentrate. Look at it. And then ask yourself this question. Step 2. Do you see something? Something, I don't know what it is, but do you see something and that something's derivative anywhere in the integrand? So I see a couple of you nodding. So does someone tell me? I heard sine, is that what I heard? Did someone say that?
Yeah. Yes.
So everyone sees a sine x in here, right? And what is the derivative of sine x? Cosine x, right?
Cosine.
Do you see a cosine x also?
Yes.
Okay, so look at step 1 and 2. We looked at the integrand. We did see something in its derivative. We saw sine of x, and we saw its derivative also, cosine of x, right? Now, couldn't I have done it the other way around? Could I have looked at that integrand and said, oh, I see cosine x, and the derivative of that is sine x, or negative sine x, right?
Yes.
But do you see negative sine x?
No.
No, I don't see negative sine x. So let's continue to step 3. Look at what step 3 says. The derivative that we're thinking of in our minds, it should appear in the numerator and not be trapped. Okay, so I'm going to write it down. Someone said sine x was the something, right? And then the derivative of that is cosine x. That was its derivative. And now we're saying to ourselves, is that cosine in the numerator? So is that cosine x in the numerator where we see it? It is, right? Is it trapped? In other words, is it underneath the square root, or is it being raised to a power or anything like that?
No.
No. So as long as the derivative is in the numerator and it's not trapped, we can continue. The next thing is to keep in mind that the derivative might be off by a constant. And that would be okay. Now, is our derivative off by a constant? It's not, right?
Yes.
No.
We have sine x, the derivative of sine x is cosine x. We're not off by a constant. It's exactly the derivative of sine, right?
Oh, okay.
You'll see as I do another example how that step 4 comes into play. So step 5 would be to actually start the u substitution method, which is on the side over here, we are going to let u be equal to the something. So I'm going to write u is sine x. Okay, so I'm actually making a u substitution right now. I'm letting u be sine x. The next step is to take the derivative of u with respect to x. And what is the derivative of u with respect to x? Just cosine x, right?
Move the
The
dx
next
over.
thing I'm going to do is I'm going to multiply both sides by the differential dx. And now comes the important part. Does everyone see that I can rewrite this original integral as y'all see that that's just me rewriting it, right? And now I'm going to start to play a little game. Do y'all see that this cosine x dx matches up exactly here?
Yep.
So what could I replace everything in yellow with?
du.
Du. Okay, and then I can replace this sine x with what?
U.
U. So I'm going to rewrite the whole problem. I'm going to get rid of things and replace them with things that have u's in them, thus making a u substitution. This will become 1 over 1 plus what?
U squared.
U squared times cosine x dx, which is just
du.
Du.
u. And now do you see we have transformed this integral that used to be in terms of x now into an integral that's in terms of u? And do you recognize that? Do you know the antiderivative of 1 over 1 plus u squared?
Arctangent
Arctangent of what?
of u.
Of u plus a constant, right? But what was u?
Sine
Sine
x.
x.
Sine x. And that's what we said it was going to be, right? That's what we said it was going to be. We need to do a few more of these, don't you think?
I always had this question about u substitution, but why isn't the du affected by the algebraic rule of not being able to, like, for example, you said we couldn't, like, when we separated the equation up top, the integral of cosine x over 1 plus sine squared x into 1 over 1 plus sine squared x and cosine x. Why
I know
couldn't,
exactly what you're asking me. So the reason is because we are not trying, when we're going from this step to here, right? We are not finding the antiderivative of each one of these separately. What we're saying is that all of this is we're trying to find the antiderivative of all of it, including the du. Now, maybe it'll help if I do this. What if we take the derivative of this? The derivative of that is 1 over 1 plus u squared times now the derivative of u, right? Right? That's du. But the derivative of du with respect to itself is a 1. So it's really like a 1. So it's the chain rule. It's the actual chain rule that's happening here. And it's not, so it's not us trying to undo a product. This du is always just that little piece at the end of the chain rule that falls out. In fact, for us, du is actually not du, it's cosine x dx. Let's try and squeeze another one in. I don't have a whole lot of time. I'm just trying to figure out if I should go hard here or not. I don't want to. I'm going to take it a little bit easy here. Jeez. Wow. All right, so in an effort to maximize our time here, I'll tell you right now that there's nothing you can do to that algebraically to use the power rule, right? So we don't have it. The only thing we have is the only other thing on the plate right now, which is U sub. So does anybody see something in its derivative?
X squared.
X squared. What's the derivative of x squared?
2x.
2x. Okay, I see a 4x. Is that okay? According to the steps over here?
Yeah.
The derivative might be off by a constant, and that's okay. All right? So you said x squared. Does everyone agree? Now let me ask you. You said x squared. Could I have done x squared plus 1?
I don't think so, because you have a power, like a chain rule, because it's under the square root.
No, don't grab the square root. I'm saying you said x squared, right? I agreed with that.
Yes.
Like the derivative of x squared would be 2x, and we're off by a constant. We have a 4x. But could you have grabbed a little bit more than the x squared? Could you have done the x squared and the plus 1?
Yes,
What would the
because
derivative of x squared plus 1 be?
it'd just be 2x.
The same thing.
2x.
Right?
Yeah,
It would still be 2x. So the trick here is to try and your something should be as much as you can possibly get without going too far. Like you wouldn't, let me just write down. We could have said u is x squared. That would have been fine. We could have said u was x squared plus 1. That would have been fine. But could we have set u to be the square root of x squared plus 1? Well, think about the derivatives of these. Du dx here would be 2x. Du dx here would be still 2x. But the derivative here would be chain rule, right? That would be like 1 over 2 roots of x squared plus 1 times 2x. So that would be too much. If I let that be my something, its derivative is too complicated. Does that make sense?
Yep.
So it's like this fine line. You don't want to pick too much, but you don't want to pick not enough. You want to pick as much as you possibly can. So I'm going to get rid of these two, and let's go with this one. Okay? I'm really running low on time. So now what I'm going to do, this part's important. I'm going to rewrite this problem like this. I like to do this, kind of split things apart. Now, look carefully. I need to get rid of some of this stuff. It's getting in my way. I'm just going to rewrite that. So we had let u be x squared plus 1. We took the derivative with respect to x and got 2x. And then we multiplied both sides by dx. And now we're trying to play this little game where we match things up. And I hope that you all see that we have a 2x dx here, but over here we have a 4x dx. And they don't match, do they? We're off by a constant.
We can take a 2 out of the integral.
We could take a 2 out of the integral. We could do that. And that would be a completely legitimate algebraic move. I'm going to do it a little different, though. I'm just going to go work with this. And I'm just going to hit both sides of this with a 2, because it's an equation. So I'm going to make this 2 du equals 4x dx. You see that? I just doubled both sides. And now 4x dx matches 4x dx exactly. And I'm ready to rewrite the integral. Integral 1 over the square root of. Now we had made a substitution that x squared plus 1 was going to be the u, right? So this is going to be square root of u. And then times, what does the 4x dx become?
2 du.
2 du. Everything's in terms of u. Did it get any better? Is this something we can handle? It sure is. Okay, so what did I do here? Rewrote the square root of u as u to the 1/2. I brought that up, right? I brought it up. And now I can use the power rule. That makes sense? I'm not done, but it's time for the antiderivative. The 2 will come. 1 over -1/2 plus 1, u to the -1/2 plus 1 plus some constant. I went ahead and cleaned all that up real quickly. And my last step is to get back to what u was. Replace u with what it was. And u was x squared plus 1. So this becomes the square root of x squared plus 1 plus c. I had to go kind of quick because I was running out of time. We are going to get plenty more practice with this. All right, next class we'll do more. If you want to try and start doing the homework, you can. Notice that I assign 1 through 36 all. That's because there's no such thing as doing too much homework at this point. Like, the more practice, the better. All right. Okay, so I've got to end.
I think you assigned 1 till 36 odd.
Did I? Oh, on the sheet, is it all or odd?
Yes, it says odd on the sheet.
You sure? Right here?
Oh,
Substitution.
I saw a antiderivative. My
Are you
bad.
looking? Okay. All right, so that's it. We're not officially done with substitution. We need to do more examples. Okay, we just got our feet in the water with this. That's it. Y'all have a good weekend. Enjoy your Labor Day weekend. Monday is a holiday. I will see you on Tuesday. Yeah.
Bye-bye.
you.
See ya.
You too, sir. Thank you.
Thank
Okay.
you. Take care.
Have a nice
I've
weekend.
got a few minutes if anyone has any questions.
So I know you said the du was part of the integration. That's why it's not here anymore, right?
That's right. I like to kind of think about it like,
That's just what's tripping me up right now is just that
Yeah.
just disappearing.
I understand. That causes a lot of people problems. It's kind of like this. It's kind of like, maybe I can do it this way. Let's go back to the example I gave earlier. Let's say y equals x squared. And we are taking the derivative with respect to x on both sides. You just get 2x. And then I write dy equals 2x dx. Multiply both sides by the differential. And now I ask you, what's the antiderivative of each one? So what's the antiderivative of y? I'm sorry, the antiderivative of the derivative of y. So this kind of stands for like the derivative of y. So what's the antiderivative of the derivative?
Just y.
Just y. Okay, so that goes back. So it's almost like I did this. I said, okay, take the antiderivative of that, right? And then I'm asking you to do the same thing on the other side. Now you see that notation? Do you see it?
Does it cancel?
It's there. It's like a chain rule. It's just part of the expression. So that should go back to x squared, right?
Yeah.
You don't have to account for that.
Okay.
I know it's weird.
That is, it's a little weird, but yeah, no, I'm getting what you're laying down. Okay.
Yeah. I'll think about if there's another way I can say that or express that makes more sense. It's always been an issue. It's a difficult thing to make sense.
Okay.
It's a notation thing. I mean, it's a notation.
Yeah, it's just notation. It's not technically a value.
Yeah, you're not actually taking the antiderivative of it because it's not. It's almost like this is really just a 1, but it's holding place value in terms of it's keeping track of your variable. And when we do a substitution, like when you come back up here.
So you have to use the variable. Okay.
Let me see. Where's the one we did with the cosine? Where was it? Where is it? Where's the one I did with cosine? It disappeared. Oh, there it is. Okay. So right here, at this point right here, I'm telling you right now that this
one made more sense. Yeah, like the du disappearing here, that one made more sense.
Okay. But du is actually not just a 1. It's not, it's actually this. I mean, that's what it is. See, it's like when we take the derivative of this, the first thing that happens is the 1/1 plus this square, this thing in here squared. But then you have to do chain rule. When you take derivative of the sine x, that's where you get the cosine x dx from. Yeah, I wouldn't try and overanalyze it because I think you might drive yourself mad with it. Look at it more like it's just keeping track of the variable and it's just notation, all right?
Okay.
But we use it when we're doing the substitution, right? Because we've used it, when we do the substitution, we're trying to match these things up, right? This dx has to be included in what we're matching. Like we have to have that dx there.
Okay.
Yeah.
I'll sleep on it and do the homework.
Yeah, don't overanalyze it at this point. We can address it a little more later.
I need to do that. Okay. All right. Thank you.
Okay, no problem.
Have a good one.
You too.